talk. There'll be a, well, as yesterday we mentioned a schedule change. So the second talk this morning will be the development of a high resolution AGCM in LASG IAP. It will be given by Dr. Qing.
Okay, thanks. Thanks for inviting me here for the workshop. It's my great pleasure to introduce our model development work. Today, I'm going to talk about the development of a high resolution AGCM at IAP LASG. It's our lab within the institute. We also would like to thank Wei Chang from Albany and JP from National Taiwan University give us great support on radiation scheme and macrophysics. And we also would like to thank Dr. S.J. Lin to give us great help on our finite volume dynamic core. Okay, this is outline of my talk. So first, I'm gonna introduce the finite volume AGCM of IAP LASG. We call it FAMIL model. Second, I'm going to show the global energy water balance characteristic from the FAMIL. Actually, this just a paper published online on GEMS last week. Third, I'm going to show the preliminary result from our high resolution modeling. Actually, since a lot of physical scheme will keep update scheme, so only some preliminary result from here. And I would like highlight some ongoing work to discuss possible cooperation here. And last, I give brief summary. Okay, first introduction to the model. We named FAMIL model. We have been developing this model more than 10 years. The earliest version is a special model about 4-degree horizontal resolution in 1998. At that time, I'm still undergraduate student. I'm joining the modeling team in the second generation of the special model. The horizontal resolution is about 200 kilometers, 2 degree by 2 degree, and the vertical layer has been improved from 9 vertical layer to 26 vertical layer. The current version I'm going to show you here is the newest version of the model. It's a FAMIL model. We use the finite volume dynamic core. The highest horizontal resolution is 1/4 degree, and the highest vertical resolution is 64. The model top at 0.01 millibar. Okay, this is the horizontal and vertical resolution of this model. I just give a brief introduction. We have 2-degree model, 1-degree model, half-degree model, and a 1/4 degree model. Finite volume, we use finite volume dynamic core on cubosphere grid. And the vertical resolution, I have 3 choices. One is 38 vertical layer, model top, and 1 millibar, and 6 transfer layer, 7 layer, and 0.1 millibar, and 640 layer model top, and 0.1 millibar. We try to capture the QBO in this version. Well, we only have a semi-annual oscillation, we call SAO, but we still miss the QBO. Yesterday, SJ talked maybe the too strong damping might kill the QBO. Well, we're still working on this issue. And the whole model is running on Tianhe 1 supercomputer. So it's quite a while we don't use the Tianhe 2, because Tianhe 2 have more CPU, have more computing resources. The major reason for this is that Tianhe 1 give us very good price. They give us 50% off, so we only pay half price. That's why we use Tianhe 1, not Tianhe 2. Okay, but we also compare with the speed. We run our model on both supercomputer, the Tianhe-2, with the same number of CPU, Tianhe-2 could be 30 to 40 faster than Tianhe-1 with the same amount of CPU. Okay, maybe we have more funding, we can move from Tianhe-1 to Tianhe-2. Okay. This is the configuration of our model. Previous version we use special model. Now we switch to finite volume dynamic core, and this is our model physics. We have for boundary layer with non-local boundary layer scheme. Recently, we have also testing UW scheme. And the cumulus, we have TD cumulus scheme, and we also test batch update from batch hold 2008 study. And for macrophysics, we have one more macrophysics and current coverage with JP and Wei Qiang working on a two-moment macrophysics to involve effect from the aerosol and radiation. We use RRTMG and gravity wave, and land model we use NCAR CLM2. The whole model are driven by NCAR coupler. Our AGCM is one atmospheric component of the climate system. We call it FGO3, the third generation of couple model, and we plan to use this couple model to excuse me. We plan to use this couple model for the coming CMAP6 project. Okay, how model computer performance on the Tianhe computer? We have tested the whole model on Tianhe-1 computer. It have achievement of use more than 10,000 core on this super, have very good model speed, and we also test model input and output efficient. Since some people just argue that Tianhe have I/O problem, we also tested our whole model system on this platform. It's get a pretty good result. Okay, the next part I'm going to show our recent paper on GEMS. Is talk about the global energy and water balance. The key point in this study is firstly the description of the new generation model developed in our lab and which is designed for CMAP6. And the second point, we evaluation the simulated global energy water balance in FEMIL. The third is identification of the possible solution to reduce bias from these evaluations. Okay. Now the motivation. Why we look at the energy and the water cycle? Because we think the energy cycle and the hydrologic cycle, water balance is one of the most important factors in climate system. Yesterday, Dr. Robert has showed a similar figure. Use Yuki model to check the effect of the horizontal resolution. Well, in our study, we don't check the effect of resolution, but we just check whether model is right or not, because we have a lot of updates from both from dynamic core and model physics. So we want to see whether model can capture this number or not. How we achieve energy conservation and water balance? It's a pretty challenge, actually. Some modeler don't want to show it, because even you check each model process or model physics, there are a lot of places you cannot make energy conservation and water balance. I mean, each time step for each column. So what we did here, we check each module, each physical parameterization, including PPL scheme, boundary layer scheme, convection, cloud, radiation, gravity drag, and we add all together to fix a lot of not conserve energy and water balance. Eventually, what we got here, the left panel is energy, right panel is water balance. And up panel from each model fix different color instead of different physical module. And the bottom panel are total result. If you look at the order for energy, we have -10 order conservation. For water, we have -100 order water balance. So model did a pretty good job to guarantee the both energy and water cycle. It's very useful, or the long-term simulation gonna benefit from this conservation. Okay, I'm showing the result from the model. We achieved, here is the global annual mean energy budget. I'm going to show this 10 variable. Top of atmosphere is solar down, solar up, thermal up. In surface, solar down, solar up, solar net, thermal down, thermal up, light heat, and sensible heat. And for comparison, we use the previous studies, both previous study, RPCC's result, satellite data, and real analysis. We also include the mountain model mean from 22 CMAP 5 models, and the circle is for our model's result. Generally speaking, model did a pretty good job to capture almost all variables except for these two variables, the fourth one and the sixth one. Okay, here. The blue line is IPCC, and this arrow bar. And our model result, this one. Our model result is for this variable, it's behind color arrow bar, and for these variables, you also have kind of bias here. We make deep understanding related with bias, and we found all these bias are related with the simulation of the cloud, especially for low-level cloud. There's a difference between our model and the satellite data result. We can see clearly our model is failed to simulate the marine stratocumulus cloud. Then they're going to generate the bias I've shown in previous slides. Okay, in the last of my talk, I'm going to show some ongoing work. This problem will be at least reduced a lot with the update from boundary layer scheme. Okay. Now, still in this paper, we also check the water balance. We think this is one of the most important variable for climate modeling. And this for our model in GPCP, CMAP, 2 real analysis, and we also calculate 16 mountain model mean from CMAP 5 model, not 22, because some models, they don't release the result for evaporation, so we only got 15 models result. And our result, E minus P, even is better than mountain model mean. Of course, the real analysis, they don't conserve this E minus P term. Okay, as request by reviewer, we also show the diurnal cycle. Now the resolution is about 2 degrees, and this is diurnal amplitude. Model did a pretty good job to capture amplitude, but the phase simulated in our model be 2 or 4 hour leading by the compared with earlier compared with the Qing observations. Okay, next I'm going to show the preliminary result from our high resolution modeling. Some of the results we still make tuning, so I don't want to. I only want to show some solid result. Okay, the first question: why we need to go to high resolution? There are a lot of reasons, but For us, particularly for Asia Monsoon region, we think the topograph forcing is one important forcing. If you look at 2 degree, 1 degree, half degree, quarter degree topography, you can a lot of difference, especially over East Asia region. If you look at Taiwan Century Mountain, in quarter degree very high, but in 2 degree, there's no mountain here. Okay. Now look at the model's result from 2 degree, half degree, and 2 degree, 1 degree, and half degree. For the quarter degree, I haven't shown here because we're still tuning this model, so we don't want to show it because there are a lot of updates in model physics. After I finish the update, we're going to show the result. You look at the model results from 2 degree, 1 degree, and half degree. You clearly see the precipitation intensity got enhanced, especially over the topography regions. That means the high resolution does improve the simulation around this region, but we also fail to capture one of the most important rain belt. We call it Meiyu in Japan, Baiwu rain belt over there. That's probably due to this only AGCM, not a fully coupled model. Also, you look at South China Sea, it will be getting better. And the following slides is just from 110 to 120 region. We look at the annual cycle precipitation over East Asia region. I just showed the domain. 110 to 120 is the longitudes. This from CMIP data. Yesterday there are talk about this behavior. In observations, their spring rain has occurred before the onset of monsoon. It's pretty unique. In the higher resolution, I would call here is a half degree model, clear reproduce this phenomenon, and that will be better precipitation compared with the lower resolution. And for the monsoon, northward march, this version is better, but the bias is still there. We miss the Meiyu-Baiwu front during the boring summer season. Okay, next, intensity frequency analysis. We look at the both precipitation and evaporation in different resolution. 2 degree, 1 degree, half degree, and see the intensity of the precipitation is enhanced, which is consistent with previous talks. But for evaporation, it doesn't change a lot. I think it's also reasonable. Okay, here I'll talk about the ongoing work on FEMIA, since there are still some bias, and we are also develop some of module. The first is a collaboration with JP from Taiwan University. We try to build and evaluate a two-moment stratiform cloud scheme called CLR. It's a bark water two-moment mixed phase cloud. And we want to use this scheme or this module to study direct and indirect effect also on stratiform cloud. Because during the Asia, especially for China, we have a lot of aerosol, so we need to take account of this process in our model. And this is a flow chart of the scheme in our model. Okay, oops. And here I also would point out that currently we use prescribed aerosol in the model. Now, Dr. DAY2 just working on the aerosol model. Later on, we're going to have an online aerosol model to use for macro physics scheme. Okay. Another ongoing work related with bias bias I show in my previous slides. That's this marine stratocumulus cloud bias, and we try to improve the low-level simulation in our model. in this preliminary diagnosis, we also see we miss this cloud. So how we improve this? In previous version, we use non-local PPL. Now we modify turbulence scheme, cloud cover, parameterization, and cumulus convection, and look at the results. This is a control run. It's from previous version, and this new runs we just did recently. I can see in the new version, model success to simulate this tilted structure. And if you look at the radial humidity in previous version, they're not well mixed. But in the new version, for below the boundary layer, they're well mixed. And if you look at the cloud, this new version, you see the cloud marine cumulus cloud occurred, but in control run it's missed. Although it's pretty good. It shows some improvement, not only for low cloud, but also for precipitation. If you look at our control version, there's still a positive bias. But look at the current new versions, they are pretty similar to observations. That's it. We also have some improvement. And we hope this improvement might improve the simulation for our couple model. We think this region is very important for the double ITC related with double ITCZ bias. But we haven't checked yet. Once we freeze the AGCM, we're going to move to the couple version. Since all the models are running with coupler, so it's pretty easy for us to switch to the coupling run. Okay, the next we are working on is MJO. These observations, this is our spectral models result from CMAP file. You can see we don't have any eastward propagation. Okay, now we make some. Well, first we look at our final volume. They share the same physical module. So for the MJO, we also don't see any eastward propagation. But we modify the cumulus parameterization, try to reduce convective precipitation. The eastward propagation is getting better. Okay, it's getting better. We hope in our couple version, this word propagation will getting better and better. Okay, this is a plan for our couple model. We'll try to make a long-term projection with our Earth system model, FGO3, with 2 degree, and long-term projection with the climate system model version for 1 degree resolution, and the near-term projection with a couple model about half degree, and we run standard alone AGCM with a quarter degree for the CMAP 6. Okay, this is the last slide I would introduce here. This global monsoon MIP we propose for CMIP 6. This proposed by Clever collaborated with our lab. Dr. Tianjun Zhou lead this project. And there's 4 scientific questions related 4 tasks. We hope modeling group may participate in this model comparison project. The first scientific question I will lead here due to the limit. I don't want to go to the detail. I would emphasize this. The first task actually is joint activity with high resolution MIP. Dr. Roberts just gave the talk yesterday. Okay, this is a brief summary. First, I describe our new generation AGCM developed in IAP LASG with design for CMAP 6. And the second evaluation, the simulate global energy and water balance in FAMIL. And I also show preliminary results from our 2 degree to half degree resolution. And the ongoing work shows the low cloud simulation are significantly improved in the new versions. Okay, and in particular for representation of marine subcumulus cloud. And also I show some global monsoon MIP for CMIP 6. Hope to draw your attention. Thank you for your attention. I'll stop here, take question.
Yeah. Any question for Dr. Paul?
I have a question about the energy conservation. In the energy conservation, do you apply correction or by the scheme itself is conserved?
Yeah, we only scheme itself.
The scheme itself?
Yeah.
For example, the cumulus parameterization. After, if the scheme is constructed good enough, it should precisely conserve vertical integrated enthalpy. So like when you check this, you sum each, the output from each, physics scheme. So in the end, you have this precise, almost precise conservation. But did you check individual component?
In our work, we check each module and each time step in each column to make energy conserve. In each time step.
By the scheme itself, it's. You don't, for example, if you look at the Carey-Manuel's convection scheme, in the very end, they have applied a separate conservation, try to make sure the scheme itself conserve. But that's not based on numerical, design. You just force it. In the end, the residual be redistributed across the entire column. So that's different from the scheme. You could apply a separate energy
actually, we use the TDIC to make sure model is there's no any additional sink or source for energy and water.
Right, but you can do that.
The scheme itself should conserve itself. Yeah, that's what we did.
We can talk about.
Yeah, we can talk later.
Michael?
So you talked about currently still tuning the 25-kilometer model. Will you retune the lower resolutions once you're happy with the 25-kilometer, or will you have the models have different tunings at different resolutions? So will they all be kind of consistent, or will each model be kind of different from the other?
Oh, actually, it's from one version of the model. They share the same model physics. There are no only some parameter for macrophysics, cumulus, or the damping in dynamic core, they are different. All other factor or model are same.
Any other question?
Back to this figure or energy conservation, yes. It looks like the energy conserved, but now you have too much low clouds, right? So that would cause us problem in energy balance. So after you tune your model to have less cloud, to have more cloud, right? Then that will change your radiation quite seriously, right? So what you do?
It's very good question. Actually, it's kind of tricky for modeler. The model top balance will be last issue we're going to solve before coupling or after coupling. After we finish all tuning process, then we move to the model top issues. Yeah, that's our philosophy to tune the model.
If you look at this figure, the atmospheric absorption, that's 79. That's 79. The atmospheric absorption at the far left, in the left figure. I'm wondering, in your model, did you ever check that? Since I don't know, Marcus, did you check in your model how much is that number? Do you get? It's 79. The atmospheric absorption, since that's related to the total global mean precipitation. In our model, we have something like 3-4 watt below that value. But there's a lot of uncertainty about that.
Yeah.
But that has something related to the global mean precipitation, because that's atmospheric absorption. You look at a lot of this is flux.
Yeah.
This is essentially flux divergence. I don't know if you explicitly calculate that. This 79, that number.
Yeah, actually we put the arrow bar here, and also we put the previous study just to illustrate there are a lot of uncertainty in these numbers. If our model is within this uncertainty, I think it's acceptable. That's our thinking.
Yeah, so looking at our diagram, we have about 70, 71 absorbed, so it's a bit low, yeah.
Yeah.
It may be why we get too much shortwave at the surface, because there's not enough absorbed
Right,
yeah,
right.
through the atmosphere.
Okay, any other question? If not, so let's conclude the topic 2 and have the tea break. And thanks again for all the speakers in topic 2.